we talked about the end of the last lecture, what goes into K. And there's really three things that we think about. The frequency factor, which is simply, just think of it as a probability. The probability of the compounds colliding with each other in the right orientation for a favorable reaction and with enough energy to start making and breaking bonds. Ultimately, what you want to make is this activated complex, this transition complex, which is very, very high energy because you've got bonds breaking and bonds forming. So it takes a lot of energy to get there. Right? But once you're there, you can slide down the top of the hill either forwards or backwards. And that hill is kind of diagrammed here. All right, so there's the double dagger. That's your transition state. And you can slide down either way. But you cannot make products until you've reached the top of the hill. Now, we talked a little bit about how things might change that would increase, make a faster rate or a slower rate, for example. We talked about increasing the temperature. Increasing the temperature increases the kinetic energy. So what's that going to do as far as the rate is concerned? Is it going to make the rate faster or the rate slower? Lots of energy. It's going to make it faster. But you're adding energy to the system, so think of that as adding to the activation energy. You're making it easier to get to the top of that peak, to the transition state. So let's fix that. Let's just say easier to achieve activation energy. How about that? Does that make it better? And thereby, the reaction rate is going to increase. Now, if we can lower the activation energy, that's also going to make the reaction go faster, right? Because now it takes less energy to get to the top of that hill. That's what happens when we add a catalyst. If you increase the concentration of the reactants, that's also, it's not going to lower the activation energy, but it's going to make it easier to get to the activation energy. All right, so now that we have that set, all right, start thinking about those three variables and how they affect the rate. Now, the Arrhenius equation is a mathematical form of exactly that thought process. Here's the rate constant. That we all know and love. And here are the three things that factor into it. There's the frequency factor. The activation energy, and of course the temperature, which we measure in Kelvin. And looky here, we've got R. Remember R? That's the same, that's the gas constant R. Now this will be in joules because we're measuring, we have energy, activation energy. All right, but don't worry, we're not going to actually be doing any calculations at all with the Arrhenius equation. Now, if you follow this in the textbook takes you through a whole bunch of calculations, several sections, or probably a long section. And just like what we did with the integrated rate laws, it turns it into a straight line. And when you turn something into a straight line, you can extract all sorts of information from the y-intercept and the slope. All right? But we're not going to do any of that mathematics in this class. You can thank me at the end. All right? I think math is very important in this class, but I also think this is a chemistry class and we don't need to spend all of our time just working on math, and rearrangements and logarithms and algebra. But you should still be able to look at this equation and get a lot of information out of it, just like what we've been discussing. So if we, for example, take a look at what's written on the bottom here. So I should say this is collectively. And if the rate's going to go faster, we'll just take a look at what this is. And actually, let me write this in more clearly. This is E, Euler's number, e to the power of negative activation energy over RT. Now, if you know anything about exponents, whether it's E or whether it's 10 to the power of, all right, if it's a negative exponent, What is that number with respect to 1? Is it greater than 1 or less than 1? It's always less than 1. Okay? So a negative exponent is always going to be a number that's less than 1. Now A, just think of A as a scalar. It's some frequency factor. We're not going to be dealing with it at all. Just think about it empirically in your mind, what it means. But that's just a multiplier, all right? E to the power of. So what did we say? What happens when you increase the temperature? What happens to the rate? What happens to the rate constant? It increases. So let's just do this. You increase the temperature, and we know that the rate increases. Can we get that from the Arrhenius equation? Well, take a look. Temperature is in the denominator, which means that the exponent, as the temperature increases, the negative exponent gets smaller and smaller and smaller. All right? Because the denominator is increasing. That means e to the power of negative something, that gets smaller and smaller and smaller. That really means that the final value gets closer to 1. It never gets higher than 1, but it's actually increasing. Do you all see how that is? I mean, rate increases because e to the power of 1 over t increases. And it keeps doing that up to 1. It never gets greater than 1. If you don't believe me, just plug some numbers in your calculator when you get home. If you lower the activation energy, right, and that's exactly what we were thinking about on this previous slide. Add a catalyst, which is going to lower the activation energy, which means it takes less energy to get to the transition state, which means the rate's going to go faster. Okay? But the activation energy, that's in the numerator. So as that number gets smaller and smaller, it's the same deal, right? The e to the power of negative EA, that's going to get smaller and smaller, so the number gets closer and closer to 1. The value actually increases. So, like I said, we're not going to do any calculations, but I want you to be familiar with the Arrhenius equation, what variables it expresses, and you can actually even just look at it to remind yourself of what these trends are going to be. All right, so when the activation energy is low, we're going to have a large K. That means it's a fast reaction. Oh, it says fast right here. Fast forward reaction. Now, let's be specific now. We're talking about forward reactions and reverse reactions, because when we get to the next chapter, equilibrium, the reactions can go forward and backwards. All right? Gone are the days when any reaction that we look at in this class only goes in the forward direction. Not anymore. So here's a simple reaction. This is one of the photochemical smog reactions that we have. Now, the forward direction really means as written, kind of like what we did with the spontaneity type questions, as written. So if we look at this reaction profile, once again, where we have all reactants on the left and all products on the right, and we take a look at the progress of the reaction, or what I've been calling the reaction coordinate, we can see there's a very, very tiny, well, if I zoom in, you really can't read it, can you? That's what happens when you copy and paste from the textbook. A very, very small but measurable activation energy here, right? It's a positive 10.44 kilojoules per mole, okay? But it's a pretty tiny hump, so it doesn't need to get much to get to the top, which is the transition phase, or the transition state. And once it's at the top, it can either fall backwards and turn back into reactants, or it can resolve in the forward direction and make products. Now, if you look at the delta energy, remember this is all a state function, whether that's free energy or enthalpy or whatever, we're not specifying. Clearly, this is a very favorable process, right? You would expect it to be spontaneous, just looking at this curve, which means delta G would be negative, right? Products minus reactants, that's negative. If it was enthalpy, it would be exothermic, negative value. But that's going in the forward direction. If we look at the reverse, so here, let's just These two profiles are just the reverse of each other. The one on the right is showing the same reaction going backwards. Take a look at the activation energy going backwards. Now, the hump that it has to overcome, the hill that it has to climb, is much greater for the reactants to actually turn back into products. That takes 210 kilojoules per mole to go in the reverse direction. Okay? So that's a very, very high activation energy to go in reverse, so that's going to give you a very, very small K, which is a slow. Oops, this should say reverse. Well, okay, it says forward reaction because now I've switched the reactions. Okay. All right, now these are going to be hand in hand. So whatever happens in the forward direction, the opposite's going to happen in the reverse direction. So usually, if the forward reaction is fast, so let's say here's K for the forward direction. So I'm going to do K sub F. So that's the rate constant for the forward reaction, right? If that's high, so if K sub F is high, that means the reaction is fast. That also means that the reverse, all right? So K for the reverse reaction is going to be low, which means that reverse reaction is going to be slow. And that should be common sense. That's the same concept when we were working with spontaneity. If the forward reaction is spontaneous, then the reverse reaction under the same conditions is non-spontaneous. Now there's a special case that you'll see from time to time in these, and you'll see this also when you go on to take biochemistry and look at a lot of biochemical reactions. You'll find that the rate for the reverse reaction and the forward reaction are very, very close. One's not high, and therefore the reverse isn't low. They're both very, very similar. So I'm going to call this a special case. That's called fast and reversible. Right? This is where the K for the forward reaction is very, very close to the K of the reverse reaction. This also happens when the activation energy for both is very, very low. You can imagine that there are cases where the activation energy is very, very high for both of them. So this is, I shouldn't even put this in quotation, in parentheses. I should put this as an and. All right, where the rates forward and reverse rate constants are about the same, and the activation energy for both is low. That's a special case. We'll use the double-headed arrow to signify that. And the way we're going to interpret that is when we have a reaction that's called fast and reversible, what that really means then is that if you have reactants there, you'll also have products. And if you have products present, you're also going to have reactants. It's as if you start with one and instantly you have both of them. All right, there's no favoritism here. So let's write this down as if reactant is present, then instantly the product is present too. And of course, vice versa. So now we're going to come back to one of the concepts that we started with at the beginning of this chapter, which was looking at a reaction, trying to figure out what's the actual molecular mechanism of how the molecules interact and in what proportions to form a transition state, which then will resolve into the products. And this is where we looked at, I think this is an example of one of the first ones that we looked at. And you might propose a model where one possible mechanism was where one molecule of NO2 collides with one molecule of CO. That forms a transition complex, and that then resolves into the products. And what would that look like? Now, you can't do this on your slides, but I can do it here. All right, so I'm gonna razzle dazzle you. All right, so just take a look at the screen. In this proposed mechanism, we're going to take one molecule of NO2. Here it is. I'm going to grab it, all right, and bring it over here, and it's going to collide with the one molecule of CO. All right, so let's put our little dotted. All right, so we're going to form a transition complex here. And then in that transition complex, when it resolves, let's see if I can do this. We're going to take, oh, no, we need to take the bottom one. We're going to take the bottom one, and when it resolves now, this guy is going to be bonded here, and then this one's left alone, and that gives us, that's what the products are. Okay? So that was one step mechanism. And you can read that right off of the stoichiometry. Okay? So this mechanism that we're proposing, where we have one molecule of NO2 combines with one molecule of CO to give us the products, this is a single step mechanism. Now a new term for you, okay? Vocabulary. Any single step mechanism that we propose for our overall molecular model, this is what we were going to call an elementary step. If this elementary step, if it's correct, then the experimental rate that we would find, the experimental rate law that we derive from the actual data would match the stoichiometry. And what I mean by that is the stoichiometry here would be the rate would be equal to K times the concentration of NO2 raised to the first power times the concentration of CO raised to the first power. This is a more formal way to state what we already went through on the first lecture in this chapter, where we just talked about, oh, well, if we double the rate of one, we expect the rate to double. And if we double the rate of the concentration, if we double the concentration of NO2, we would predict the rate to double. Or if we doubled the concentration of CO, we would predict that the rate would double. But we found experimentally that wasn't the case. One second. That's the same as now making this formal statement. Any single step that we propose, we're now going to call that an elementary step. And if the elementary step is the actual mechanism, then it will match the experimentally derived rate law if we just look at the stoichiometry of the elementary step. So if we were to, let's say that this as written, all right, that's an elementary step, it's a one-step thing. If that's the actual mechanism, then we would predict that when we did the experiment, we would find K is equal to NO2 concentration raised to the first power, because there's a 1 here, times CO raised to the first power. We already did that, right? This is a perfectly reasonable hypothesis, right? Now, if you remember from the earlier lectures, we already know this model isn't right. But we did the experiment. The experimental data did not match it. So we need to come up with another proposal. We need a new hypothesis. And what do we need to do with that hypothesis? Test it. Now, there's no other single-step mechanisms to come up with. Because you can't say, well, NO2 is going to magically turn into NO and CO2. Where'd the carbon come from? Okay? So we need to now think of a multi-step mechanism and test it. And that's where things get a little interesting. Okay? So here is a multi-step. Mechanism. And again, this is just a proposal. We can think of anything that we want as a proposal. It's kind of like the state functions, right? It doesn't matter what route you take to get from state 1 to state 2, right? As long as you get there in the end, it doesn't matter what route you took. This is kind of the same thing, except now in our proposal, something has to match what we find experimentally. That's what gives us support that our proposed hypothesis is in fact correct. Well, it won't ever prove that it's correct. It's just consistent with it being correct. So let's come up with a multi-step mechanism. Now, in each multi-step mechanism, each step is an elementary step. Okay? So each step is an elementary step. Now here I have it diagrammed out for you. Blue is for nitrogen, and red is for oxygen, and black is for carbon. All right, you can see elementary step 1 looks like this. And I've got 2 molecules of NO2 are going to collide with each other in just the right way, right? That's the A factor, the frequency factor. Just the right way, with enough energy, and going to then resolve into 1 molecule of something new, NO3, and a molecule of NO. Okay, so we're inventing some new things. That's okay. That's just in step 1. Now I have a new elementary step 2, where I propose that now we're going to take 1 molecule of NO3 and combine that with a molecule of CO. That's new. We haven't seen that yet, but it's in our reaction up on top. Okay, that's where the carbon's coming from. And now when I have a molecule of NO3 and it collides with a molecule of carbon monoxide in just the right orientation, all right, with enough energy, it will now form a transition state, which can resolve into 1 molecule of NO2 plus 1 molecule of CO2. Okay? And these add up. Using the reaction arrow as our equal sign, okay, we find that we've got NO3. Now, NO3 is not listed anywhere up here. There's no NO3 here. But I've introduced that in my hypothesis. But in doing so, it's created in step 1, and it's consumed in step 2. So it never actually is there. I mean, you can try to trap it. You can try to isolate it, all right? But you don't have to. It's as much as is created in my hypothesized step 1 gets consumed in my hypothesized step 2. But it allows me to get from the beginning to the end in a different way. Okay? There's a special word for these things that are produced in one step and consumed in another. It's called an intermediate. One thing, though, then, for any proposed mechanism like this, all right, a requirement is that they need to add up to the reaction that we're trying to describe. So let's make sure we do that. So we have 2 NO2 plus CO goes to, wait, there's a mistake here. Where's my mistake? Oh, no, there's no mistake. It goes to NO2 plus CO2, but notice that I have 2 NO2 left and one NO2 on the right. Wait a minute.
You just need double of everything.
No. This is supposed to come out just right. Oh, there's an NO. I didn't put the NO here. Now it'll work. Because we've got 2 NO2, 1 NO2, so this NO2 goes away, okay? And that gives us what we started with, right? So that is a requirement. Proposed elementary steps must add up. I'll just put that in quotation marks because we're not really adding anything. Add up to the reaction that we're trying to describe. Okay? Now, the question becomes, how do we prove that this is right? So anytime you have 2 steps, let's say you're, well, actually, before we even get there, let's go ahead, because I told you earlier that if the elementary step is the correct mechanism, then the rate law that you would write from it, based on its stoichiometry, would match what we find experimentally. Remember that? So let's go ahead and write, what would the rate laws of these 2 elementary steps be, just based on the stoichiometry? So the first one, all right, the rate of reaction 1 would be equal to the rate constant, K, some K, times what? Times the concentration of NO2 squared. Right? And that's it. There's only one product. There's only one reactant. How about for the second elementary step? What's the rate law for step 2? It's going to be equal to K times the concentration of NO3 raised to the first power times the concentration of CO raised to the first power. So now we have 2 proposed rate laws. The one that's correct, if any of them are correct, will have to match our experimentally derived rate law. Now, does anybody happen to remember what the experimentally derived rate law was when we did this? Go look back in your notes. What was it? Zero power.
Yeah.
Which is the same as just saying the rate, because that's 1, right? Anything raised to the 0 power is 1. So that's the same as saying that the rate is NO2 squared. That's what we found. So does that match either of our 2? It does. It does. Yay! But what about elementary step 2? It doesn't match that. Okay? So there's one more concept to overlay on this exercise for you. And that is what happens when you have 2 steps. Okay? Here's the overall reaction. Okay? Elementary step 1, we propose 2 elementary steps. But let's go ahead and write the rate law from each elementary step. So if we take a look, the rate law for the first step is equal to K times the concentration of the reactant raised to the power of its stoichiometric coefficient. Right? And for the second step, the rate would be equal to the concentration of NO3 raised to the first power times the concentration of CO raised to the first power. If we looked at the reaction up here, if we had done that at the very beginning, we would have come up with a rate law is equal to K times NO2 times CO, right? That's just based on the coefficients. So now we have 3 proposed rate laws, right? One that I got from the full equation, as if that were the only step, and then two more from a multi-step proposal, and from each of those steps, I've proposed what the rate law would be based on the stoichiometric coefficients. And here's why you can't just do it and say that's what the rate law is, because we actually did the experiment. When we did the experiment, I mean, we didn't do it, but we analyzed data from the experiment and found that the experimentally determined rate law was the rate is equal to K times the concentration of NO2 squared. That's what was measured. Okay? So now that we're hypothesizing the mechanism, we want a mechanism where the hypothesized rate law actually matches the experimentally determined rate law. So of these choices, which choice, 1, 2, or 3, which one matches the experimentally determined rate law? 2 does. Okay? This one matches. The fact that that matches, this supports the 2-step proposed mechanism. Doesn't prove it, but it supports it. But we have to imagine, though, how does it support it when the 2-step mechanism has another rate law, number 3. So if the proposed multi-step mechanism is right, what do we do about that third rate law? What does it mean? The first step, step 1, okay, that has the rate law equal to K NO2 squared. Step 2 happens here. Step 2 has the rate law of, sorry, I meant to put a K here. K NO3 to the first power, CO to the first power. And what can we say about the activation energies here? Here's activation energy for step 1, and here's activation energy for step 2. Which one has the higher activation energy? Step 1, right? Which has the slower rate? Step 1. Remember, the rate, sorry, not the rate constant, K, Arrhenius equation, is equal to the frequency, it's equal to the frequency factor times e to the power of activation energy divided by RT. So as the activation energy increases, K decreases. Right? And if K decreases, that means the rate gets slower. So higher activation energy, K is lower, which means that the reaction is slower. You just got to get used to thinking about these things. We're not even putting numbers to this. We're just saying faster and slower. Okay? Let's imagine a really complex multi-step. Let's imagine we have step 1, step 2, step 3. This is from, going from A to B. And let's say step 4 is really, really slow. And then we have step 5, and then we finally make B. It's a 5-step process. The overall rate of going from A to B doesn't matter how fast 1, 2, 3, or 5 is. All that matters is the slowest step. That slowest step is going to determine what the overall.
Any faster than
It can't be any. Yeah, it can't be any stronger than the weakest link. It can't be any faster than the slowest step. All right. So that's what's determining the overall rate. So what we have here then is to explain. Well, what's up with this rate law? Well, this is the fast step, and this is the slow step. We don't have any other proof that step 2, mechanism 2, is correct, okay? But it's consistent. What we do have data to support is that elementary step 1 is slow, and our imaginary elementary step 2 is fast, and that's our proposed mechanism, right? It's valid. So that also explains why we can be zero order with respect to carbon dioxide. If you remember this, right? Zero order. How can it be zero order, folks? Well, this is how. It's still, here it is. It's still a reactant, all right? But it doesn't enter the reaction until the fast step. So it doesn't factor in. Doesn't matter how much or how little CO, I mean, there has to be some CO. If we change the concentration of it, that's not impacting K. That's not impacting the rate because it's part of the fast step. That's how you can get zero order rate kinetics. So that reminds me then to remind you that what we have here, NO3 is made in step 1 and it's consumed in step 2. We learned that that's what an intermediate is. And by the way, that's another reason that this proposed rate law can't be right for step 2. Because look what it has in it. It has the intermediate in it. An intermediate is something that you didn't add to the reaction. The intermediate is produced from the first step and then it's consumed in a later step. So you can never have a valid rate law that has an intermediate in it. It's got to have the reactants in it. So let's write a little note here. A valid rate law cannot have an intermediate in it. But that's okay. It's part of the fast step, and that's consistent with it being a fast step. So, now that we've gone over that, let's practice a little bit. I've got 2 practices here, but let's have you guys try the first one, or the second one. The first one actually has something to do with it. So let's just do 13.10. Which of the following mechanisms is consistent with the energy profile shown in this figure? So, right from the get-go, you should recognize what these curves mean, activation energy and reactants and products. How many reactions is this reaction coordinate describing? 1, 2, or 3? 2, all right? So you're looking for a proposal that has 3 steps. So we can rule out B. B only has 1 step. We're looking for something with 2 steps. And all that we're told, we've got A plus B goes to C for A, and then C goes to D, slow and fast. So if we just look at A, what's the intermediate? A, B, C, or D?
C.
C is the intermediate. What's the intermediate in step C?
C again.
It's still C. That's right. C is still the intermediate. So what do you think? It's either A or C. Well, slow and fast. So why A? Because the first step is slow. And why does that mean that it's A? Because here's the first step. We make one transition state. Remember, the top of this is always this transition state. So let's put our double dagger. That's that's transition state number 1. And this is transition state number 2. But look at the activation energies. It's higher to get the first one. And once we've made the first one, now that's where the intermediate, that's where C is. That's our intermediate. C is made when you resolve the first transition state into products. But we're not done. That C then gets consumed in the next step, but that's a fast step because it has a small activation energy. Okay? Very good. Let's look at this second one, because the second one's a little tricky. Same deal. Can you rule out any of these right off the bat? Which one can you rule out? D, for the same reason. Clearly, it's a 2-step process that's being diagrammed, so we can rule out the 1-step mechanism. We have 2 to choose from. The first step is slow, the second step is fast, or the first step is fast and the second step is slow. Look at your activation energies. Here's the activation energy for the first step. Here's the activation energy for the second step. So which is the fast step? 1 is the fast step, which means you'd want to pick C. Okay? But the problem with C is, what is the problem with C? 2A goes to B, and then B goes to C. Why is that a problem? So if we were to write a rate law for these, let's go back and write the rate law for these. Let's go back to the first one that we did. Right? If we said that this is the right answer, so if we were to write then the rate law that we would find experimentally from this, what would it be? The rate is equal to K times what? A to the first power times B to the first power. So it's first order with respect to A, it's first order with respect to B, it's second order overall. So you've all correctly shown that C is the right one for the first exercise. So what would the rate law be? K. Well, the rate law comes from the slowest step, remember? For your proposed mechanism, the rate law has to match what you find experimentally. So the converse of that is, if this is the right mechanism, then the rate law we would get from the slow step should match what we find experimentally. So what's the rate law of the slow step? B, and that's it, right?
We can't use it if it has an intermediate.
That's right. That's the problem. So that can't be the rate law, even though in this proposed mechanism, that's the slow step, all right? And the way we reconcile that, so that's something that I told you, when you see this written, this is fast and reversible. Reversible with an I or with an A? I, okay. So here, slide whiplash. Where did I talk about that? Here, right down here. Fast and reversible. We'll use the double-headed arrow, special, okay? That's when these are equal, the forward and the reverse rates are fairly equal to each other, and they're both very, very fast. When you have that special case, we use this double-headed arrow, and that basically means that the minute that you have products formed, you also have reactants, or the minute that reactants are there, you have products. Meaning that if you've got one, you instantly have the other one. They're freely interchangeable. So really, that also then explains this as a valid proposal, because if we have B present there, well, that's the same as having 2A. This is the same as 2A, which means it's A raised to the second power, because if this is present, then 2A was present, and they're interchangeable. Okay? So it's just a little bit of sleight of hand over an otherwise very formal logical progression. And you'll see this in biology all the time, you'll see it in chemistry all the time, and we'll see it in equilibrium all the time as well. What it really means, I don't want to tell you what it really means. Delta G is close to 0, but we're not going to go there yet. I want to try to keep this relatively simple. Okay, so we don't need to go over this slide. This is just a bunch of words that summarizes the main logical themes that we've been working through. Okay, so this is just a summary slide. You can read these for yourself. And in fact, this next slide is a summary as well, but I want to add a few more things to the summary. So a few new terms to explain things to you. So we have this idea now that we have individual steps, these elementary steps, and our proposed mechanism will either be a single step or it's a multi-step. But regardless, the rate law that we get from the coefficients have to match what we have experimentally. Now, there's a few new terms to describe. In this term of molecularity, I don't know really why we emphasize it, but we do. It just simply describes what's happening to the molecules in the reaction that you're writing the rate law for. So, for example, when you have a single-step mechanism, okay, that means that the rate law is the same as you can get from the coefficients in the proposed reaction. Okay? And there's various ways you can do this. So we could have one reaction where there's just A that goes to products. Right? And if that's the case, then the rate law, if that's the correct mechanism, then the rate law would simply be rate is equal to K times the concentration of A, raised to the first power. Okay? And we would call that, we've been calling it first order, but in this case, this whole reaction, this is what we would call unimolecular. Whereas we could imagine a bimolecular reaction where two things have to hit each other in just the right way to make products. And we can imagine there's two ways to do that. We can have two molecules of A that have to combine to form products. Or we can have two different molecules, A plus B, combine into products. And each one has their own rate law, right? For the top one, the rate would be K times A to the second power. And the bottom one would be the rate is equal to K times the concentration of A times the concentration of B. Now for both of those, we would describe them as the reaction overall is second order, but using this new terminology, here let's just write second order, and overall this is what we would describe as a bimolecular, not bio, bimolecular reaction. Two molecules collide in the right orientation with the right energies to create the transition state, which then resolves. If we have termolecular, that's when we have three things. Well, I can imagine I have three molecules of A that have to combine in just the right way to make products. That rate law would be rate is equal to K times A raised to the third power. Or I can have two molecules of A combine with one molecule of B to make products. That rate law would be K times concentration of A squared times the concentration of B. Or we could have A plus B plus C. All have to combine at the same time in the right orientation with the right energies to give us products. That would be the rate is equal to K times the concentration of A times the concentration of B times the concentration of C. Okay? It's pretty straightforward. All three of these are what we would call third order overall. And with this concept of molecularity, we would call this a termolecular reaction. Now, as you might imagine, termolecular reactions are much more rare. They're not very common. And you're basically requiring the system, three things have to collide in just the right orientation with just the right energies. So that's rarer than having two things collide, or even just one thing. So overall, the termoleculars are less likely because we need all three things need to collide favorably. Just a few more terms to overlay over these concepts. These last two things, we've already gone over this several times, right? I hope you get the logic now of what we do with the multi-step mechanism. All right, here's the summary description of them. But when you have a multi-step, you've got intermediates, okay? So you don't have intermediates if it's a single-step reaction. And intermediates, sometimes they're hard to prove. Sometimes you can capture them and measure them, but most of the time you just have to infer that they're there and it all works out. And again, you support your hypothesis by measuring experimentally what the rate is, and everything needs to match. Okay? So we don't need to go over those last two steps, or those last two summaries anymore. So here's our overall equation. And here is what we experimentally measured. That's the rate law. So, evaluate the proposed mechanism. Is it consistent? And if it's consistent, which is the rate determining step? Discuss.
Explain it.
Step 1 matches the experimental.
Because step 1 matches the experimental. Well, does it? Let's find out. So let's write the rate laws. This is how you do this, okay? So first we have to evaluate. If this proposed mechanism is right, we need to write out what would the rate laws be for each step. The elementary step 1 would have a rate law of K is equal to the concentration of hydrogen gas to the first power times the concentration of NO raised to the second power. The elementary step 2 would have a rate law of K is equal to concentration of hydrogen gas to the first power times the concentration of N2O raised to the first power. And N2O doesn't even appear in our overall reaction. So this must be an intermediate if it's correct. Here I'll just put I for intermediate. Well, no, let's write it out. Intermediate. Okay? And the proposed rate law for elementary step 1 matches, I just wrote it backwards, it matches what we found experimentally. And it doesn't contain an intermediate. So far, so good. But something else then we're asked to, which is the rate determining step, if this one's right. It's number 1. That's the slow step. This is the slow step. This is the rate determining step. And how do we know that? Because it matches. Rate determining. By this analogy. All right? The rate determining step, the one that determines the overall rate, is the slowest step. Okay, good. I think you're getting this. If all I gave you was that and not the proposed mechanism, how would we know what the elementary steps are? Well, you'd have to propose them. All right? And when you propose the elementary steps, you need to make sure that one of them has to match the experimentally observed rate law. And there's something else that you need to make sure of when you propose a multi-step mechanism. It has to add up to the original one that you're trying to describe. Let's make sure that this one adds up. What cancels out here? Well, I'm looking for an intermediate. N2O cancels with N2O. And we've got 2 hydrogens here, so that's 2H2. We've got 2NO. And that goes to 1 N2 and 2 oxygens. 2 H2O, sorry. So it does. So those are your 2 requirements. They have to add up, and one of them has to have a proposed rate law that matches the experimental. And then it's up to you to figure it out. You have to make a proposal, and one of them has to match. All right, let's talk about catalysts then. We already talked a lot about catalysts and what they do. Let's just do that a little bit more, but let me remind you. So, in a catalyst, the main job, well, actually, here's the main definition, right? It's a substance that increases the rate, but it doesn't get consumed in the process. So let's just write out what that means. So here's a reaction. A plus B goes to C plus D. Let's say that's my reaction. And it goes at some rate. All right? If I add a catalyst, the catalyst is going to increase that rate, but in the process, it actually does not get consumed in the reaction. So as much as I added in the beginning of the reaction, the same amount is present at the end of the reaction. All right, so the catalyst increases the rate. Now remember, the rate constant is equal to A times e to the power of negative activation energy over RT. The way that it increases the rate is by decreasing the activation energy. By decreasing the activation energy. That's how the rate is increased. Now, how do we magically decrease the activation energy? I mean, what does that mean? What does activation energy mean to you? I keep saying it, we keep talking about it. What does it mean? The energy you need to start the process, that's true. But what does it mean for the actual atoms that are, where the bonds are being broken and formed in the transition state? What does activation energy mean in that context?
Correct.
Yeah. The energy required for that transition state to exist. Remember that? The transition state is sitting way up here, right? This is an energy scale, okay? It takes a lot of energy for that transition state to even exist. If you don't have that energy, it's so unstable that you can never make it. And if you can never make the transition state, you can never resolve it into products. So the way a catalyst does this, the catalyst actually will interact with the transition state and stabilize it. And it's not magic. I mean, we don't have time to go into an intricate example, but there are bonds that are made. There are stabilizing forces that the catalyst provides so that it takes less energy to keep that transition state stable. It lowers the amount of excess energy or external energy necessary to stabilize it, because by interacting with the catalyst, it's already more stable. Does that make sense? So if we put a catalyst in here, the profile will look like this. Right? Because of this, it doesn't need as much external energy to stabilize the transition state, because it's interacting with the catalyst. But notice that the starting point and the end point stays the same. All right, that's a common theme. We're lowering the activation energy, but the delta, the change in energy in this case, or it may be change in free energy, it could be change in enthalpy, it could be change in any state function, right? That stays the same. That's why they're state functions. But by lowering the activation energy, we can get from state 1 to state 2 much more quickly. Okay? Now there's a couple other terms here for you. Homogeneous, heterogeneous, and biological catalysts. Those are pretty simple. That just talks about the phase. Whether it's homogeneous, that just means that the catalyst is in the same phase, whether it's solid, liquid, or gas, as the reactants. And if it's heterogeneous, that just means it's in a different phase. Like on your automobiles, the catalytic converter, right? That helps to reduce a lot of the nasty gases that your car puts out, right? The gases are in the gas phase. The catalytic converter is in the solid phase. So a catalytic converter in a car, right? That's solid phase and the gas phase. So it's a heterogeneous catalyst. And then there's a biological catalyst. We have a special name for those. Enzymes. When you take biochemistry, you'll learn all sorts of enzymes. And that's what they do. Enzymes are proteins that catalyze reactions. The reactions would happen on their own, maybe, maybe not, but they catalyze it so they increase the rate. So along with that, we have multiple steps in our reaction mechanism. Remember that we had things that were produced in the reaction and then were consumed in the next step. What are those called?
Intermediates.
Intermediates. All right? So you should know what an intermediate is. And of course, catalysts are present at the beginning of the reaction and they're present at the end of the reaction. So they weren't used. Or if they are used, so here is a proposed mechanism, a proposed two-step mechanism for a reaction. And the reaction is mixing hydrogen peroxide, which is H2O2, with potassium iodide. So one of the requirements for the two-step mechanism is that it has to add up to the overall reaction. Okay? So rather than us predicting what those products would be, let's just assume that this proposal is right, then it should add up to what the overall reaction is. And so let's add these two together, and let's recognize, in fact, in doing this, let's identify what's the catalyst and what's the intermediate, and how do you know? Let's do the intermediate first. Which one's an intermediate, and how do you know? IO minus is an intermediate, and how do you know? Because it's what? It's in the products and the reactants, but specifically, it's in the products of the first reaction and then in the reactants of the second one. So it's produced in one reaction and consumed in another as part of a multi-step process. So you never see it. You don't start with it, and it's not there at the end. It's made and consumed, which means it cancels out. So that means that the intermediate was IO minus. All right, and which one's a catalyst? I'll do the catalyst in red. And how do you know which one's a catalyst?
Minus.
I minus. And how do you know that I minus is a catalyst? Because it was there when you started and it's there when you ended. And it wasn't used up in the reaction. Mole per mole, okay? We start with 1 mole of I minus, we end up with 1 mole of I minus. So it cancels out as well. Okay? So now we can see how things add up, because everything else that's left just adds up. So we've got 2 hydrogen peroxides. So that's going to be our overall reaction. I'll just write it down below here. And then we've got 2 H2Os. Well, let's put our states of matter because that counts. Liquid plus O2. That's the overall reaction. And remember, that's one of the requirements when you propose a multi-step process. And what would be the rate law? If this proposed mechanism is correct, what would the rate law be and why? It's determined by the slow step. Remember, that's the rate limiting step. Doesn't matter how fast the other ones go, you can only get this reaction to go as fast as the slowest step in the process. That's what you would measure experimentally. Remember, the rate law is what you measure experimentally. So if this mechanism is correct, then whatever we get from the slowest step, if we just read it off of the coefficients, that should match what we see experimentally. Go ahead. All right, so here's our last example of a catalyst, okay? And this is looking at ozone naturally breaking down into molecular oxygen. This is a reaction that happens all the time. This normally happens pretty slow. And thank goodness for that, because ozone protects you, right? Ozone absorbs ultraviolet radiation from the sun. So you've all heard of the ozone layer, and you've all heard about the hole in the ozone layer and how the hole was getting bigger and bigger and bigger until we did something about it, and now the hole, actually, this is showing you, this graph is showing you how the hole in the ozone layer was getting bigger and bigger and bigger until people realized, hey, if this keeps happening, we're all going to die because we can't stop the ultraviolet radiation from coming in. We're all going to get sunburns and all the plants are going to die. We won't have any food. And this is a big deal, folks. We need to do something about it. right? What was the big deal? The big deal had to do with these things, CFCs, chloro, fluoro, chlorofluorocarbons, or CFCs. These were like propellants and aerosols and air conditioning refrigerants, and they leak out into the atmosphere. And the problem with these CFCs is they create atomic chlorine gas in the atmosphere. That's a free radical, okay? That's chlorine, not diatomic. We won't sing the diatomic song here. It's a free radical with an unpaired electron, and those are nasty things. And in this case, the chlorine acts as a catalyst for that reaction. It makes the ozone going to molecular oxygen that much faster. Okay? And here is two reactions now. Right? It's a two-step process. Here's the chlorine as a catalyst reacting with ozone to give us an intermediate, ClO. I'm going to put an I here because that's an intermediate. This is a two-step process. Intermediate. And one molecule of O2. And then in a second step, we have our intermediate gets consumed as it reacts with another molecule of O3 to regenerate our free radical chlorine into oxygens. Now let's just look at this, all right? We've got that cancels with that, the catalyst cancels with the catalyst, and what do we have left? We have 2O3 gas turns into 3O2 gas. It's the same reaction that we had up above. Okay? But look at these reaction profiles. The one in blue is uncatalyzed. Look at that activation energy. It's really, really high. So it's slow. Normally, it's a slow process. But when we have those free radicals around, the chlorine free radical, it catalyzes the reaction. And even though it's a two-step process here, right, it goes much, much faster now. The activation energy is much, much lower. So it goes very, very fast. All right? So some terminology here, okay? We already know that the intermediate, we know what that does, right? The intermediate in this case was ClO, and it's produced and consumed in the same reaction. But now we have the catalyst. The catalyst was present at the beginning, and it was present at the end. Even though I canceled it out here, okay, there's a difference. The catalyst is present at the beginning and at the end. So in one sense, they both don't factor into the final reaction. It goes faster. Okay. But they are really two different things. You should be able to identify in a set of reactions like this which one's the catalyst and which one is the intermediate, because they do have different behaviors. Now, just to finish this story, okay, I told you, people realized that this was happening. They said, hey, we're in trouble. We better do something about this. All right? And they did. The industries changed. The air conditioning industry changed the refrigerants. All of the companies that were making products that used aerosol cans, they changed the propellant. They reduced dramatically the number of CFCs that were getting into the atmosphere. And look what happened to the curve. It leveled out, and now it's starting to go down. Yay us! We did it. Now, can we do this with carbon dioxide levels? It's the same argument. And look at the chaos that our world is in now, trying to deal with carbon dioxide levels, right? This was only, 30 years ago? Maybe? 20 or 30 years ago, right? Everybody recognized there was a problem here, and we all did something about it. And it's the same deal. The economics are the same. Whole jobs, whole industries had to change, okay? Same arguments now. What's different? I don't want to get into it. All right, but we did it then, we can do it again. Save. Now, I would say save the planet. I got news for you. The planet is going to be just fine. All right? We might not be here to enjoy it, but the planet will get along just fine. It will recover once we're long gone. All right, I don't want to leave this on a happy